Alright, in this video I want to talk about the idea of apparent weight and artificial gravity. I'm going to start off by the idea that scales, such as the bathroom scale, read apparent weight of an object. So it's not always accurate. It's usually accurate in our situation because we're not accelerating. When we step on the scale, we are at constant velocity, we're in equilibrium, it's not like we are floating and accelerating up or down through the ground. So most of our scales read apparent weight, and that is fine for most of our purposes. But in weird situations such as if you were to take your bathroom scale into an elevator, you would see that your weight would fluctuate. And as we'll see, you really want to calculate your weight as you are accelerating down. The definition for apparent weight is the force that the object exerts on a scale with which it is in contact with. In most cases, we'll call this the normal force. So the normal force does change based off of contact. What we'll see, though, is as acceleration or the net acceleration of object goes up, weight or apparent weight is greater, and as acceleration goes down, or if something is accelerating down, the weight is less. And as we'll see, this will have a great impact on what the idea of weightlessness is. So in our example, we have an elevator, we have a bathroom scale, and we have a person on that bathroom scale. And for this purpose, let's pretend that the acceleration, the net acceleration, is up. If we draw a free body diagram, we'll have the force of gravity here. And for predictive reasons, the normal force will be longer than the force of gravity. You can see that already that this has to be the case because if the net acceleration is up, the normal force vector has to be greater than the force of gravity vector. We know in general the equation for the force of gravity, it is the mass times the acceleration due to gravity. If we were to do a net force problem of this, we really don't have any net force in the x direction, so the net force in the y direction is all we need. And we know that the net force in the y direction is the normal force minus the force of gravity. And since it is accelerating, this is not equal to 0, this is equal to mass times acceleration. If we're now to substitute Fg is equal to mg, we'll get Fn minus mg is equal to ma. And then from there, if we know that by definition the force that the object exerts on a scale with which it is in contact with is the normal force, or what we call the apparent weight, you'll see that the normal force, the contact force, is actually greater. You are in more contact with the surface if you are accelerating up. All right. And then for the specific example, so for example, if your acceleration is equal to negative 9.8 meters per second squared, you'll see that in this case, your acceleration will cancel out with your acceleration due to gravity. Your normal force equals 0. So in the case where acceleration is the acceleration of the actual elevator, which means the elevator essentially gets cut. So the acceleration of that is equal to g. That is what we call weightlessness. Now, another example is what happens in the situation of this cylindrical type of object that, has a track on it. Imagine if this is actually, a circle and there's a little person that can walk all the way around in a circle. This is actually what some satellites are simulated to be. If you're sitting in a circle, this is where we can actually simulate artificial gravity. And if you want to take a look at this, this is example 13 in chapter 5. Artificial gravity. And artificial gravity specifically that we simulate with acceleration due to circular motion. So the reason why we started this video with apparent weight is because we figured out, okay, normal force is actually the force of contact. Can we simulate the same force of contact if we have something spinning around in a circle? The answer is yes. We'll see that if you have an object moving, say for example this person that has a tangential velocity v, and he or she is a certain distance from the center of the object, so there's a radius here. In example 13, that radius is actually 1700 meters. What speed is required for the acceleration, the centripetal acceleration, to equal the acceleration of Earth? So if you take a look at this one again, once again, if we were to do a free body diagram of this person, the only force that we would want on him in this case is a centripetal force that equals the force of gravity. So we want this to mimic, the force of gravity to mimic what we would find on Earth. And so if that's the case, our centripetal force is given to be mv squared over r. Our force of gravity is equal to m times g. And if we solve for v, we can cancel out the m's. We get v is equal to rg, or the square root of rg. Really interesting. At a certain speed with a radius, we know our gravity should be 9.81 meters per second squared. We can actually get how fast you need to go in order to accelerate at that speed. So given our 1700 meters and 9.81, the speed this person would have to spin around on this kind of spacecraft looking thing would be around 130 meters per second.